Hello. Today we'll have a session on the life cycle of stars, star formation, and stellar evolution. So, what are stars? Stars are huge balls of gas radiating high amounts of energy due to nuclear fusion going on at its center. There are certain important questions which come to our mind, which are stars born? Most people ask often whether stars have always been there or are they created at some epoch. Yeah, so are stars born? Do stars evolve? And do stars die? Short answer to this is yes. Stars are born, they do evolve, and they die in different forms depending on the initial mass and chemical composition. The very fact that they are radiating tremendous amount of energy constantly indicates that they have to evolve. And there should be a time when this energy source should end up. So let's see how these stars are born and where are they born. So these are some pictures of stellar nurseries. These are images of giant molecular clouds, which is the raw material from which stars are formed. These extend over very large distances, over many light years across. So these giant molecular clouds are low density clouds. They are about 10,000 atoms per centimeter cube. They're very cold, say 10 to 20 Kelvin. They are mostly made up of hydrogen, about 75%, helium, about 20 to 25%, and a little bit of heavy elements, less than 2%. These molecular clouds in different regions of the universe, they would be of different composition. This is a very average estimate which I have given in a solar neighborhood. So if these molecular clouds have sufficient mass and low temperature, then it collapses under its own gravity. There are two forces acting on the system. One is the gravity, which tries to collapse the cloud, and the pressure, the thermal pressure from within, which tries to expand it. So there is a tug of war between these two forces. So if, like in low mass clouds, the gravity is less and the pressure is more, then the cloud will expand. Gravity loses and pressure wins. And in a high mass cloud where gravity is high and pressure is low, gravity compresses the cloud and gravity wins and the cloud contracts to start on. Here's a criteria which will give you what kind of clouds do we need? What should be the masses of clouds required for them to collapse under its own gravity? This is called Jeans mass. In gas clouds, the kinetic energy is due to the motion of atoms which make up the cloud. And suppose there are these capital N atoms in the cloud. The kinetic energy is given by K equal to N 3 by 2 kT. And the gravitational potential is given by U, which is minus 3 by 5 gm squared by R. There's a very important theorem called the visual theorem, which can be derived very easily in mathematics using the moments of inertia in differentiating with respect to t twice and equating it. So what we get is this result, which is 2k plus u equal to 0, twice kinetic energy plus potential energy 0 for a virialized system. Hence, taking k from above and u from here, we get back we get this expression 3n kt equal to 3 by 5 gm square by r. If you want to have the cloud to collapse, we would require the left-hand side to be smaller, because this is the term which is going to expand the cloud. There's a thermal energy, and on the right side is the gravitational potential which is squeezing it. So for it to dominate, your 3 by 5 gm square by r should be greater than 3n kt. And if we take this n, the number of particles in the mass, as the total mass of the cloud divided by the mass of each atom or particle, then assuming the cloud has constant density, the size of the cloud can be related to the mass and density by this expression. N is taken as m by m, where m is the mass of the giant molecular cloud, and small m is the mass of the atoms. And your r is given as 3m by 4 rho square to the power of 1 by 3. Substituting this here, we get estimates of Jean's mass, which is given here, 5 kt by gm to 3 by 2 to the power of 3 by 2, and 3/4 pi rho to the power of half, square root of this. And if the cloud mass is greater than this Jean's mass, then it will lead to collapse. So the cloud will collapse if the mass is bigger than Jean's mass. This is called the Jean's criterion. This is the criteria which the molecular cloud has to satisfy for it to form stars, for it to collapse under its own gravitational force and form stars. One interesting thing is stars are always formed in groups, so star clusters are formed. So as I said, there is a tug of war between the gravitational energy, gravitational force, and the thermal energy which is trying to expand it. Mass clouds of the order 10 to the power of 3 to 10 to the power of 5 solar masses which you require, with temperatures say 10 Kelvin, 25 Kelvin. So if you have a higher temperature, then you require a larger mass, and so on. So as the cloud gravitationally collapses, the density is increased, and even the lower mass would be sufficient for star formation to take place. So the cloud fragments, and in these fragments, stars are formed. So take home point, stars are not born in isolation, they are always born in groups, and all field stars are from clusters. Like right now our sun is a field star, it doesn't have its siblings around, but it must have been born in a cluster, and it is now ejected out from the cluster due to some dynamical effects which we shall see in the next lectures. There are other triggers of a star formation, and there are these spiral density waves, supernova, or galaxy interactions. We have a picture here of a galaxy, and these are the beautiful spiral waves. We will see what galaxies are in detail in the following lectures tomorrow. And these are called the spiral arms. And these spiral arms, we would realize, are not stationary, but they are constantly changing. It's a dynamical system where the galaxy is continuously evolving. And these spiral arms, they move. And if a spiral arm encounters a cloud, then it could compress it and lead to star formation. The other aspect is supernova. Further down in this lecture, we will know what supernovas are. In short, when a massive star explodes, a star which is, say, more than 7 or 10 times that of solar mass, after it has reached iron core, it explodes in a supernova. And if it explodes close to a molecular cloud region, then it can compress these supernova winds go and compress these clouds and can lead to triggered star formation. Another one which we shall be seeing in the following lectures is how galaxy interactions, when two galaxies come close to each other, they disturb each other, they can compress the gas in it, and they could lead to star formation. So stars are formed, one, they can form on its own if the molecular clouds are cold and massive enough, if they meet the G's criteria. They can form stars if a spiral density wave compresses the clouds. It could lead to triggered star formation. There could be a supernova triggering star formation, or there could be galaxy interaction which could lead to triggered star formation. Now coming to stars, as we see, they emit tremendous amounts of energy. For example, our sun itself is emitting about 10 to the power of 33 ergs per second. And our sun is an ordinary star. There are certain stars which are much larger than our sun, and there are certain stars which are less massive, less hotter than our sun. So they have different mechanisms of creating the energy. And the basic mechanism is nuclear fusion, in which we have the proton-proton chain reaction, where we have 4 hydrogen atoms. They come together to form helium and release energy. So if you look at the initial total mass of 4 hydrogen atoms, as you realize, hydrogen has 1 proton and 1 electron which orbits it. While to form helium, we require 2 protons, 2 neutrons at the center in the nucleus, and 2 electrons orbiting them. And if you see the mass of a helium, there is a difference between the total initial mass of these 4 hydrogen atoms, which is 6.693 into 10 to the power of minus 27 kg, and final total mass of 1 helium is 6.645 into 10 to the power of 27 kg. And there's a difference of mass which is equivalent to 0.048 into 10 to the power of minus 27 kg. By using the famous Einstein's equations E equal to mc square, this missing mass is converted to energy which is released. So this is the amount which we get when 4 hydrogen combine to form 1 helium, but there are trillions and trillions of tons of hydrogen which is being converted to helium at the center of our sun, creating tremendous amount of temperatures. As we have seen, initially the cloud starts compressing under its gravity, and the thermal pressure tries to expand it. If the cloud is big enough, then it continues to collapse the cloud, and the temperatures at the center of the cloud keep rising. Gravitational energy is converted to kinetic energy, and the temperatures rise. And when the temperatures reach say millions of degrees, then the hydrogen atoms, they fuse to form helium. Normally, when you try to squeeze matter, after a certain stage, it resists it. Yeah, depending on what's the temperature, what's the pressure, it resists it. And beyond a certain point, you can collapse it. But then electrostatic forces try to repel it. Does not allows more atoms to come too close to each other. But when the mass of the cloud is very high, the gravitational force is so much that the outward forces, the repelling forces are weaker. Hence, the nuclei fuse to form heavier elements. So, four hydrogen atoms combine. This is called proton-proton chain reaction to form helium, and energy is released. And here, yeah. So, the other important fusion reactions, other than the proton-proton chain reaction, are CNO cycle and triple alpha reaction, which occurs in other stars, in more massive stars. In our sun, proton-proton chain dominates the energy creation. So 91% of energy in our sun comes from the proton-proton chain reaction. The other ones, like I mentioned, are the CNO cycle. It's a complex series of reactions in which the transformation of carbon, nitrogen, oxygen, nitrogen, carbon facilitates the conversion of four protons to one helium nucleus and with the release of energy. So this happens in more evolved stars. The stars which have only hydrogen, which start off with only hydrogen gas, would not have CNO going on. But when certain amounts of carbon and nitrogen and oxygen are created, then the CNO cycle sets in. And it is a more energetic reaction which creates more energy. It requires more mass in the star and it creates more energy more efficiently. This happens in hotter stars. And the third one is called the triple alpha reaction, where three helium nuclei fuse to create one carbon nucleus and with the release of energy. So, and in more massive stars, you have carbon burning to form higher elements. So, what happens is initially a star starts off with molecular hydrogen gas clouds, where hydrogen fuses to form helium. And when the center of the star, it consumes the whole of hydrogen. The whole of hydrogen is converted to helium. Then the reaction stops and there is no heat creation going on while the gravity is there. So the star starts getting smaller. It contracts further. And as it contracts, the hydrogen in the outer shells get funneled into the center in the hotter regions, and this hydrogen suddenly start getting converted to helium. And also some helium atoms, they fuse to form carbon. So there's a sudden heat production and the star expands and it becomes a giant star. It becomes a huge object. It becomes a giant star. We'll come to this as we proceed further. And it lives like a giant for some time. And then it throws out its outer layers. And the inner layers, star again compresses. And as it compresses, if the mass of the star is sufficient, it can fuse helium to form carbon, and the helium slowly gets converted to carbon. And then again, when the whole of helium is consumed, the star stops creating this, and and then it collapses again if the mass is sufficiently large to form carbon fuses to form heavier elements and so on. So you get magnesium and oxygen and so on, all the way up to iron. But if the mass of the cloud is not much, then it would stop only at as a helium dwarf stars with maybe hydrogen in the outer shells. So depending on the mass of the star ends up as a white dwarf, or it continues to convert and create heavy elements all the way up till iron. So here, the purple line here indicates the main sequence. You have already uh, learnt about the HR diagram. We have temperature on the x-axis and luminosity on the y-axis. And notice that the x-axis is written in the reverse order. So 2500 is on the right side, 5000 left, and so closer to the point, this point here, we have higher temperatures, while on the edges we have lower temperatures. Luminosity is written in the proper ascending order. So most of the stars, as you have learned in the HR diagram, lie on this main sequence. The main sequence is the time when a star is in its very stable state, where it is converting hydrogen to helium. Until the time it has not converted the whole of hydrogen at its center, it sits on the main sequence. And once it's exhausted, then it moves away from the main sequence and goes to the other regions of the HR diagram, to the red giant part of the uh, planetary nebula stage, or the dwarf ones. And the lines which you see here in black are called the Henne and Hayashi tracks. And this shows how stars of different masses come and sit on the main sequence, the processes which go on. For example, around each line you'll notice is 1 solar mass star, 2 solar mass star, 3, 5, 9, and 15 solar mass. And the ones here are masses less than our sun. So look at our sun. It is coming down, indicating the luminosity is decreasing. The luminosity is here on the x-axis. So the arrow shows that the star marches down, becomes less and less luminous. What does this indicate? It indicates that the star is collapsing. The cloud is collapsing. It's not yet a star. It is a pre-main sequence stage where you have a cloud which is radiating for whatever temperature it has. And as it gets smaller, it looks fainter, because luminosity depends both on temperature and on the size. So the radius is getting smaller, hence it's becoming smaller. Then it reaches a stage where it's getting slightly horizontal, which indicates that the star is getting hotter. So that compression is leading to heating up of the cloud, and the temperatures are rising. So this is why it's moving leftwards on the scale. And then there's a slight increase. Going up slightly. So the luminosity is increasing. And then again, there's a drop in luminosity till it comes and sits. So again, you see luminosity is decreasing, temperature is increasing because it's contracting, and then luminosity is slightly rising, but the temperature is rising a lot. And then, right, so all these show that the star pulsates. It's a tug of war between the gravity and the thermal pressure. So when the gravity dominates, it becomes smaller, it gets less luminous. As it gets squeezed up, the nuclear reactions in the center become stronger. So heat is created, so it becomes big. Then it becomes big, so heat creation reduces, so again it compresses and it pulsates till finally it reaches a equilibrium where the creation of the heat at the center and emission from its surface, they become equal, and then the star becomes a stable star and sits on the main sequence. This is the time, and most of the time of its life, a star sits on the main sequence. A major portion of its life is on the main sequence. So here we have a cartoon of of a star. The core has hydrogen burning, and the temperatures, like I said, for our sun is should be 10 to 15 million degrees in the core, and it has different layers at different temperatures. The photosphere, the yellow surface of the sun which we see, is called the photosphere, and the temperature on this is about 6,000 Kelvin. Core having millions of degrees, 10 to 15 million, and the photosphere is 6,000 Kelvin. And in between there's a gradient. As you go from core to outside, the temperature reduces. And due to this thermal gradient, there is a flow of energy from the center to the surface of the star. And here you see the main sequence star, and as it completes the whole hydrogen at the core gets consumed, it marches off from the main sequence and it becomes a red giant, right? I said when the reaction stops, the star collapses and suddenly expands because the hydrogen of the outer shells, they get funneled into the central outer regions and they fuse to form helium. And also helium fuses to form carbon and so on. So it expands. There's sudden creation of heat for a moment and the star expands, and what you are seeing is it is becoming big, right? And this is a point where helium ignites and the helium begins, temperatures increase, and then the helium gets exhausted and it the stage, and carbon ignites and carbon burning begins and so on. So depending on what is the mass of the star, it either stops here and then comes and sits here as a dwarf star, or it continues to form heavier elements. As for our sun has lived half its life. Presently, its age is about 4.5 billion years. And since its mass is about 1.99 into 10 to the power of 30 kilograms, it has a total lifetime of, say, 10 gigayears. So we have lived half its life. And after 4.5 billion years, the sun one day will start becoming a red giant. It will become big to engulf the whole of the orbit of Mercury, Venus, and swell up to engulf the Earth's orbit. Its radius from 1.5 million kilometers, it will become almost 150 million kilometers radius, right? And it would live like a red giant for a million years or so, billion years, and then throughout its outer shells to become a planetary nebula and end up as a white dwarf star for the center. So depending on the mass of the star, here's a cartoon which shows how it attains its onion-shaped structure. It starts off with hydrogen overall, then hydrogen at the center is converted to helium, and then helium gets converted to carbon. So center, here we have high helium at the center, hydrogen in the outer region. Then we have, if it's massive enough, then helium converts to carbon, and you have carbon at the center, helium in the inner layers, and hydrogen outside. And then carbon continues to magnesium and oxygen and so on. So you have an onion shaped structure. Then oxygen converts to neon and so on. So stars get a shell structure, and this shell structure, it depends on its mass. Very massive stars which are say 7 to 10 times solar masses, they continue this way of converting hydrogen to helium, oxygen, carbon, oxygen, so on, all the way up to iron. All the elements which you find on the periodic table up to iron are created in the centers of stars. And after iron, however massive the star may be, it cannot fuse iron to form heavier elements. Because if you see here, uh, ferrous, after it's created ferrous, it becomes an exothermic reaction, and it requires much more energy for it to form. So this can happen only, a lot more energy is there, and this comes when massive stars they blow up as supernovae. So a star which is 7 to 10 times more massive than our sun would ultimately, after it has created iron at the core and assumed the shell structure, it cannot fuse further, and it collapses and rebounds with tremendous force, uh, creating a supernova. And in supernova, all the other heavier elements which are found on the periodic table are created. So this is the timeline of the fate of our sun. It started off with a planetary nebula, a cloud of molecular hydrogen gas, which compressed to form the main sequence star. This accesses in billions of years, and it would live up to 9 billion years, and then it will start becoming unstable. Our present state is here, somewhere 4.5 billion years, and then it will become a red giant and throw off its outer regions to become a planetary nebula, and then become a white dwarf star. Yeah, and this is the march it would take on the HR diagram. This is the pre-Magman sequence star, where the cloud is collapsing, becoming less luminous. Then the nuclear reactions coming up, heating up, sitting on the main sequence, sitting here for 9 billion years, and then one fine day marching off to become a red giant and reach the asymptotic stage, become a planetary nebula, and then end up as a white dwarf star. So here's an image of a planetary nebula, the outer atmosphere of a star being ejected out from an exploding star. And these are called planetary nebula. This has nothing to do with planet formation. This is the planetary nebula is a stage where stars